In this video, we're going to look at the mechanisms of allylic bromination. So here I have a simple alkene, and we're going to do an bromination, and where the bromine is going to show up is on the carbon next to the double bond, because that is the most stable radical available in the system. So how does this work? Well, we have to start off by breaking the bromine-bromine bond. We can use some light, or you could use some heat, but one way or another, you have to form a bromine radical. So that bromine radical will come along and it'll go for the allylic CH. And so we draw a couple fishhook arrows showing the abstraction of the hydrogen, and a third fishhook arrow showing the formation of the allylic radical. So we now have this allylic radical. Now the allylic radical, of course, will then come along, find a full molecule of bromine and extract the bromine and form the final product. And of course, that gives you back the Br dot. Now this was answer C on the previous video, if you go back and look at that. So here's our we've set up our chain reaction, because now we've got our Br dot, which can go back up here and do another reaction. But of course, there's the added wrinkle of this is that the allyl radical intermediate over here is that this is a delocalized system. So this radical center is actually also delocalized into this other carbon, and that carbon can just as well do that reaction. And so it gives you the other product, which was product B back in that earlier video. So we got our two possible products here. Both of them give you a mole of bromine radical back, which can go up and complete the nature of the chain reaction. Now, a given time around this circle, you'd form either product B or C. You can't form them both in the same circuit, but you're going to be getting a mixture of these things all the time. So this is basically how the thing works. It's a pretty simple process, and it's very much like bromination that you learned last semester for simple hydrocarbons. Okay, so this is called radical chain reaction. I can't spell. Radical chain reaction. That's pretty funny. Anyway, the key thing in this that makes it work is that the Br dot is at low concentration, and you need to remember that. So the rate determining step, it turns out, is the formation of this particular radical. Once you form this radical, the bromine is not such a low concentration. This radical is so unstable, this is a pretty fast reaction compared to this one. So the slow step is this one right here. So that's the slow step. Now, the reason that's important is that that alkene, of course, you learned a different reaction for double bonds and bromine molecule, is you can just do a direct addition. Remember, you form the bromonium ion, and then the bromonium ion is opened up by the bromide coming in, and you form this product. So what are we talking about? Well, the bromine doesn't react via allylic bromination. It reacts by addition to the double bond. So how do we understand these two competing reactions? Well, it turns out it's a little complicated. But there are two competing reactions, but it turns out there are tricks that you can use to control them. So let's look at this reaction in a little more detail. This is the slow step in this reaction. And why is it the slow step? Well, it's simply because in this particular case, these are going to be both at low concentrations, because you're sitting here. This is your main reactant and the bromine. So these are your two reactants, and they start off at reasonable concentrations. But this intermediate, and this is a true intermediate, it's not a transition state, is you're going to have a very small amount of this intermediate around. And of course, you don't have excess bromide around either. So both the bromide and the bromonium ion are at low concentration. They're both at low concentration, and so if you have a step of your reaction with both reactants are at low concentration, it means the rate is very slow. If particularly so, if the original bromine concentration was low, I mean this is just going to be a slow reaction. So and essentially the key thing is two low concentrations in the same step, and it's going to be like multiplying a small number times a small number. And let's compare that to the slow reaction here. The slow reaction here was that Br dot extracting the hydrogen. And in that case, what you have is one species in low concentration. Okay, so the way to favor this reaction is to make the bromine concentration very low, because in the radical reaction, you only have to worry about one species being low. In the conventional reaction, without doesn't involve reactions, you have to worry about two species being low. So if we can keep our bromine concentration very low, which means that there's very little of it, okay, the kinetics will favor the free radical reaction, and it's simply because you don't have to worry about both species in that rate determining step. So allylic bromination is favored if the bromine concentration is very low. So how can you do that? It turns out it's really tricky to use actual bromine. So to do allylic bromination, we generally don't use bromine molecule. What we use is this new molecule, which we call NBS. NBS stands for Nbromosuccinimide. And where does that name come from? Well, this is succinimide, this cyclic amide down here, because it's a cyclic amide come from succinic acid. So succinimide, this is called, and Nbromo means that you take off the hydrogen you put on a bromine. So this is Nbromosuccinimide, and it's a source of bromine. And the way this works is really pretty clever. All right, so the first thing that happens is break a little bit of that NBr bond, okay? Or you can use some heat. Or sometimes just the impurities around is enough to give you a little bit. And sometimes you don't need to do anything intentionally, it just happens. But anyway, this will form a Br dot. And that Br dot will do the reaction. It'll extract the CH bond, and you'll get your first allyl radical. That allyl radical is going to react subsequently, but something else is going to happen here first. Is we're going to take this HBr molecule over here, and that HBr molecule is going to react with the NBS. And what happens is the nitrogen gets protonated, and the Br minus attacks the Br as a Br plus, and it makes bromine. That's really weird. NBS plus HBr makes bromine, but we didn't put any HBr into the reaction. We get the HBr because it's the product of that first CH abstraction. Now what happens? We've made that bromine. Now the radical will come and pull off a bromine off the bromine molecule and make a new Br dot, which can go up here, extract another CH, form another mole of HBr. That mole of HBr can react to the NBS, and so on. So this is a chain reaction which involves three reactions, including the reaction of NBS of HBr. So first reaction over here, second reaction down to the third, and then the product of the third is the reactant of the first. And this is the nature of a chain reaction. You have a bunch of linked reactions where the product of one is the reactant of the next. In this case, there's three reactions linked together. In the simpler cases of just using bromine for doing radical bromination, there's just two. So this is pretty neat. Three reactions linked together. Now, and so that finally completes our cycle. So this is a three-step chain reaction. The bromine concentration is always low. That's the trick, because we never build up a big concentration of this bromine. So the addition to the double bond just isn't a problem, because we kept it low. So the net reaction of all this, the net result of all this, if you want to add bromine to the double bond, you just add bromine and it'll add to the double bond. But if you want to do allylic bromination, what you do, you use NBS, which keeps that bromine concentration very low. So it seems pretty kind of complicated, but it really isn't when you put it all together. And of course, since this is allylic bromination, you of course get that second isomer, which I didn't include in this mechanism, but you have a second process down here, because you can this radical gets delocalized on this other carbon as well. So you get the second isomer. You can't get away from that. So how do you assure that allylic bromination works? you use NBS. Now, it turns out you can use NBS very easily for benzylic bromination as well. And so this reagent is a good versatile bromination reagent whenever you have some relatively weak CH bonds. Now, we're not going to ask you to do any mechanisms on the exam with radicals, but you will be asked to predict a product or products using an NBS reaction. And the secret is, of course, simply to go back to that table of bond strengths and find the weakest CH bond in your molecule, and that's the one that's going to react with the NBS to give you a bromination product. So overall, this seems complicated, but I say you don't really have to worry about the mechanism too much, but do look at the relative reactivity of various CH bonds.